Next, I'm delighted to welcome Professor Mourice Cox. Last May, I was honored to meet Mourice at the NB Spring meeting at the National Physical Laboratory in London, where he presented a lecture about GAM, the guide to the expression of uncertainty in measurements. Thank you very much, Mourice, for accepting our invitation and coming all the way from England to Israel to talk about GAM. Professor Cox joined NPL in 1968 and has worked at NPL ever since. For the last 14 years, Mourice has been a mathematical consultant to NPL. Prior to 1968, Mourice worked in industry for General Electric Company for 8 years as a mathematician. During his career, Mourice has applied mathematics widely, especially to measurement science, including areas of physics, chemistry, and biology, publishing many papers over the last 20 years. One of his main interests has been measurement uncertainty evaluation, in which subject he has made contribution to supplements to the GAM and other related guides. He has editorial responsibility for GAM revision. With NPL colleagues, he has delivered training courses on measurement uncertainty evaluation for many years in the UK and other countries, and regularly at NPL. He chairs 3 committees on statistics or measurement uncertainty, 2 of which are international. Mourice.
Thank you very much, Diamanta, for inviting me here. And thanks to Dr. Cohen, Diamanta, and Daphne for facilitating this visit. I'm very honoured. I want to talk about the GAM. It's not quite the same talk as I gave at NPL last year. I've updated it slightly, and I'll take you through it fairly quickly, bearing in mind the limits of time. The outline of the talk is to mention briefly ISO 17025. I know a lot of you work to this standard. I'm going to speak briefly about the Joint Committee for Guides in Metrology and the current work on the GAM, revising the GAM, and the supplements to the GAM. I'm going to talk about the approach being taken in revising the GAM. We're going the Bayesian way, and I'm going to try to indicate why we're going the Bayesian way, discuss some technical aspects, the consequences for national measurement institutes and industry, and a brief summary. We all know, most of us know, 17025. I want to mention a particular clause from 17025, clause 5.4.6.2, which states the following: testing labs shall have and shall apply procedures for estimating uncertainty of measurement. In certain cases, the nature of the test method may preclude rigorous, metrologically and statistically valid calculation of uncertainty of measurement. In these cases, the lab shall at least attempt to identify all the components of uncertainty and make a reasonable estimation, and shall ensure that the form of reporting of the result does not give a wrong impression of the uncertainty. So to adhere to 17025, the practitioner it's really a tall order. He's got to achieve a certain standard in adhering to 17025. And this clause can be interpreted in various ways. My interpretation is the follows: the degree of rigour needing in evaluating uncertainty measurement depends on several factors, including the requirements of the customer. So generally, to deliver a measurement result acceptable to a customer requires some degree of assurance in its quality. What does that mean? Can such assurance be given in applying the GAM, the Guide to the Expression of Uncertainty in Measurement? Degree of assurance is open to interpretation. My interpretation is that if we can provide a measurement uncertainty associated with a measurement result that has got one significant digit correct in it, that's normally acceptable. I give a simple example at the bottom of the screen. A resistance, its best estimate might be 1005.2 ohms, and the standard uncertainty associated with that resistance value is 0.5 ohms. It's pointless to deliver an uncertainty 0.527 ohms. 0.5 is perfectly adequate for most requirements, if not many requirements. And so that's the degree of rigour we want in our results, in my opinion. Certain cases might be exceptional, and we have to give them the attention they deserve. But as a general rule, one significant decimal digit is all we need to quote. The Joint Committee for Guides in Metrology, it was established just before the year 2000, in about 1997 or 1998. And the tasks of the JCGM are to maintain and promote the GUM and the VIM. You've heard both these acronyms today. There are two working groups. Working group 1 is concerned with the GUM, and working group 2 is concerned with the VIM. The JCGM is a very, very powerful organisation, particularly because it includes 8 member organisations, which comprise ISO, IEC, OIML, and the list is there for you to see. And any document produced by the JCGM, it's reviewed by all those 8 member organisations. It has to be approved by all those member organisations. If you know the ISO review process, Antonella knows it well. If you knew the ISO review process, which is a period of 5 months voting, balloting, and so on, and there's a second review of that sort of length, and the IEC adopts the same voting process. Other organisations have their own rules too. The JCGM documents so far, JCGM 100 is the GUM itself. JCGM 101 is the first supplement to the GUM concerned with the propagation of distributions by a Monte Carlo method. JCGM 102 is a multivariate version of 101. Those 3 documents have already been produced. JCGM 103, which is under development, is concerned with modelling. JCGM 104, being published, that's an introduction to measurement uncertainty and to the GUM family of documents. JCGM 105, under development, is concerned with underpinning concepts, the basics, the fundamentals of measurement uncertainty. 106 is concerned with conformity assessment. I think that was mentioned earlier today. 110 is going to give a rather complete set of examples illustrating the application of these guides, and JCGM 200 is a VIM, which we've heard about today. What about the current GUM, and what about the revision of the current GUM? The GUM was published in 1993, so it's just over 20 years old, and it served us well. Its merits have been recognised, its limitations exist, but the merits have largely outweighed the limitations. Its main merit is to provide a framework by which systematic effects and random effects, both arising from measurement of course, a consistent treatment of both those effects. But, having said that, there are 2 main limitations. There's some lack of generality of the procedure to obtain a coverage interval, or confidence interval if you like. An interval containing the value of the measure and the quantity we want to work with a stipulated probability. The second main limitation, there's little guidance in the case of more than one measure and, more than one quantity of interest. And so, with those limitations in mind, GUM Supplement 1 and GUM Supplement 2 were developed and published, rather than carrying out an extensive revision of the GUM. Here's the original GUM, published in 1993, which you can buy from ISO and you have to pay for. It costs something like $200, so it's not an inexpensive item to provide, to obtain. In 2008, the JCGM made available a free version on their internet site. You can obtain this through BIPM, through IEC, and through ISO, a number of other sites as well. The current gum. As I see it, there are four main features to the current gum. The first feature is a measurement model. You have to have a measurement model in place connecting the input quantities. These are the quantities about which we know something, about which we have some knowledge, and the output quantity, the measurand, the quantity about which we require knowledge. A measurement model relating the input quantities and the output quantity. Second feature, knowledge of the input quantities. We need best estimates of those quantities, and we need standard uncertainties of those estimates. That's to apply the current gum. Third feature, the law of propagation of uncertainty. It's based on a linearization model. One of the earlier presentations gave the LPU, law of propagation of uncertainty, and it provides a standard uncertainty of the estimate of the output quantity. The fourth feature is an assumption. The assumption that the central limit theorem of statistics applies. In other words, that the measurand can be taken as Gaussian or normal, in order to provide a coverage interval for the measurand. I'm going to talk about each of these four aspects in turn. The measurement model, we can consider the input quantities, big X1 up to big Xn, and the output quantity, the measurand, big Y. The measurement model is denoted by Y equals a function of those input quantities. It's often in mathematical form. It can be, in a complicated case, expressed by a computational algorithm, particularly when a solution of a partial differential equation or a large nonlinear least squares problem is required. And in the revised GUM, there's no substantive change from the current GUM in relation to the measurement model. The current GUM requires the user to stipulate or develop a measurement model. The revised GUM is going to be exactly the same. Example, I think it was Professor Kennett that presented exactly the same example I've got here. Example is a simple model relating three input quantities, the mass of a higher purity metal, purity as a mass fraction, and the volume of solution, to the mass concentration of a calibration standard solution. That's a very simple example of a measurement model where we have knowledge of the quantities M, P, and V on the right-hand side, and we want to deduce knowledge of the quantity gamma. Knowledge of the input quantities themselves. We have input quantities, capital X1 to capital Xn, and we have best estimates of those quantities, little x1 up to little xn. And we also have standard uncertainties, u of x1 up to u of little xn. In the revised GUM, there's a change to the way we obtain knowledge of some quantities. If one of our quantities is defined in terms of repeated indication values, we have a so-called type A evaluation of uncertainty. We handle this a different way, and I'm going to mention this a little later. The input quantities may be physical quantities like masses, lengths, resistances, and so on. Or they might correspond to correction factors, systematic effects. The u of little xi may be derived from repeated indication values, as I mentioned, type A evaluation of uncertainty, or they may be derived from other knowledge, supply specifications, tables, etc. That's the type B evaluation of uncertainty. The third aspect is the law of propagation of uncertainty. To apply this law, we need to linearize the measurement model about the best estimates of the input quantities. And I give the linearization there. And the C's in that expression, the CI, are the partial derivatives of the measurement function with respect to the input quantities evaluated at the best estimates of those quantities. And we take the best estimate of the measure rand is taken as the first term in that expansion, the linearization. In other words, the measurement function evaluated at the best estimates of the input quantities. And we take the standard uncertainty by applying the law of propagation of uncertainty. And the formula is given there, but that formula applies under the assumption the input quantities are independent. If they're correlated, we have some additional terms to that expression. Again, there's no substantive change from the current GUM. The fourth item, and this is where quite a large change is taking place in the revised GUM. The assumption is, in the current GUM, that the central limit theorem applies. And under the central limit theorem, we compute a coverage interval for the measure rand, y, given a coverage probability, say 95%. And that interval is such that the probability that the true value of y lies in the interval is 95%. And so a simple diagram illustrating just that. The assumption is, according to the central limit theorem, that y, the measure rand, the output quantity, may reasonably be described by a Gaussian distribution, normal distribution, or a t distribution if there are degrees of freedom associated with the quantity. The central limit theorem holds if n, the number of input quantities, is sufficiently large and if no one input quantity dominates. Otherwise, it may not hold. The revised GUM is changing the way in which a coverage interval is determined. It's important to recognize that fact. I'm going to make a few remarks about the need for revision of the GUM. In the Bayesian world, available knowledge about a quantity is described by a probability distribution. And whatever knowledge you have about your quantity, you embody that knowledge, you encapsulate that knowledge by a probability distribution. And the current GUM, it regards type B evaluations in exactly that way. The current GUM adopts a Bayesian view. The knowledge of this type of quantity is used to assign a probability distribution. And when you've assigned the probability distribution, you take the standard deviation of that distribution as the required standard uncertainty. So directly from that probability distribution, you can deduce the standard uncertainty. And that's been in the GUM since 1993 when it was first published. We're not changing a thing in respect of type B evaluations. But type A evaluation, we're going to change. Type A evaluation doesn't follow the rules for type B evaluation. The current GUM doesn't assign a probability distribution depending on the knowledge available of the quantity. The standard deviation is directly estimated from data and used as a standard uncertainty. As I stress, no probability distribution is assigned. And so, in that respect, a type A evaluation is frequentist because it works directly with data. It doesn't work with probabilistic concepts, but type B evaluation is Bayesian. And so there's a contrast between type A and type B evaluations. And so we thoroughly accept what's done for type B evaluations, but we don't accept what is done in the current GUM for type A evaluations. Further on the need for revision, as I said, the current GUM is a mixture of Bayesian and frequentist approaches. the approach involves, it's quite complicated in my mind, especially in the construction of a coverage interval, and the given procedure is not general enough. A Bayesian approach, those of you who know Supplement 1 and Supplement 2, I am aware that a number of you are aware of it. A Bayesian approach was used consistently throughout those documents. The consequence is that the GUM, which uses both Bayesian and frequentist approaches, isn't consistent with its supplements. This is the major motivation for the decision to revise the GUM. The approach being taken to revision, the simplest way to overcome all the difficulties and remove the lack of generality is to adopt a Bayesian view throughout. As I said, in GUM Supplement 1 and Supplement 2, knowledge-based probability distributions are assigned to the input quantities in a measurement model. For instance, if we know a quantity, if the only knowledge we have about a quantity is a lower bound and an upper bound, we assign quite naturally a rectangular distribution to that quantity. And that rectangular distribution, it's logical to assign that such a distribution, but it also follows from the principle of maximum entropy. And if we have the only knowledge about a quantity is, say, the best estimate and the standard deviation, we naturally assign a Gaussian distribution to that knowledge by employing Bayes' theorem. And so whatever knowledge we have, we use that knowledge to represent a quantity by a probability distribution. And in those supplements, we propagate those distributions through the model using a well-established procedure, Monte Carlo, which has been around a very long time. The outcome is to produce a numerical approximation to the probability distribution from the measurand, or if we have a multivariate measurand, a joint distribution. From that resultant distribution, we can compute all information we need: best estimate, standard uncertainty, coverage interval, other information if we need it. And so we see a PDF, which is a form of probability distribution, a probability density function, as a very comprehensive way to express an experimenter's knowledge, a metrologist's knowledge of the measurand. And we can extract the summary data from that PDF. I've indicated extracting the expectation, which we take as the best estimate, extracting the standard deviation, which you take as the standard uncertainty. And I also mentioned we can extract a coverage interval for any stipulated coverage probability. And this is knowledge-based. This PDF is based on our knowledge of the input quantities propagated through the model to produce knowledge of the output quantity or measurand. And so the revised GUM will pay much more attention to obtaining reliable results given the measurement model and given PDFs for the input quantities, which are established from available knowledge of those quantities. The important thing here is we don't just pluck uncertainties from the air. The uncertainties are based on knowledge we have of the quantities concerned, and we want to use that knowledge in the best way we can to deduce PDFs for the quantities involved. Reliability issues. Considering the current GUM is often interpreted as follows. We form an estimate of the measurand by evaluating the measurement model of the best estimates of the input quantities. We evaluate the associated standard uncertainty using the law of propagation of uncertainty, obtained by linearizing the model. For a given coverage probability P, we form a coverage factor K, which for 95% is K equals 2, under the assumption of normality. And we form an expanded uncertainty by simply multiplying the standard uncertainty by our k value. And that's the basis for forming a coverage interval. There's a variant for a finite degrees of freedom. For p equals 95%, we take the k factor from a t distribution rather than a normal distribution. It's important to remember some of these steps assume the measurement model can safely be linearized. In many circumstances we can justify that, but in certain areas like chemistry and biology, where uncertainties tend to be quite large, and indeed the models might be nonlinear. And it's quite an assumption to make, linearizability of the measurement model. As I'm stressing, greater attention is being paid in the revised GUM to providing reliable results. Harking back to 17025, my interpretation is we need to provide some assurance to the user, and so to give that assurance we will need to provide much more reliable results than in the past. And so a simple instance, we have one of the simplest models in the world, y equals x1 plus x2, where our knowledge of x1 encourages us to assign a rectangular distribution. Our knowledge of x2 says we should assign a t distribution, and y equals x1 plus x2 has the distribution given on the right, which is neither Gaussian, nor t, nor rectangular. It's not a defined distribution. And so we've got, in such a circumstance, to take account of the specifics of the distribution we get. Particularly in terms of computing a coverage interval, we will get a very wrong answer if we assumed the current GUM considerations. In particular, I mentioned earlier the central limit theorem, which applies for large n. N equals 2, as it is for this example, can hardly be considered large. What are the modus operandi? Revision is being carried out along the following lines. We want clarity. Of course we want clarity. We're trying to write an international guide. But clarity doesn't come easily. We've got to reconcile scientific rigor and the simplicity of the presentation. It's not easy at all to achieve. Structure, we want to stay as close as possible to the current GUM as we can. Producing a document that appears to be an evolution rather than a revolution. Level of presentation is close to that of the current GUM, and better specification when you can apply the GUM and when you should turn to the supplements to the GUM. The outcome will keep in the revised GUM, it will keep the law of propagation of uncertainty as a central concept, but it will follow a Bayesian approach for both type A and type B evaluations, giving relevant hyperlinks to the GUM supplements where necessary. Main differences from the present GUM: improved guidance on the evaluation of standard uncertainties associated with estimates of input quantities. Bayesian approach being extended to type A evaluations of uncertainty. And we see that the revised GUM will be easier to use than the current GUM, and improved guidance on determining coverage intervals. Concepts in the current GUM, and this is a revolutionary part of what we're doing, concepts in the current GUM that will go away completely are that of effective degrees of freedom and the use of the Welch-Satterthwaite formula to propagate degrees of freedom. They'll no longer be needed in the revised GUM. And we're going to include many more examples in a separate examples document, which has got the added virtue that we can update that document on a routine basis without disturbing the revised GUM itself. I must mention type A evaluation, some of the details. In the current GUM, we take the best estimate of the particular quantity as the average of a set of n repeated indications of that quantity. We take the standard uncertainty in the usual way as the standard deviation of that average, and we assign a corresponding degrees of freedom, one less than the number of repeated indication values. But that standard uncertainty is not the standard deviation obtained from a state of knowledge distribution. It's not. If we draw our n equals 6 samples from a normal distribution, the distribution we shall be assigning to the quantity concerned is a t distribution with 5 degrees of freedom, but the standard deviation of that t distribution is not the standard deviation of the sample. And so the revised GUM will rectify that situation. And I give the specific formulae here. You note that the standard uncertainty is now enlarged from the previous standard uncertainty by a factor, talking in standard uncertainty terms, a factor of the square root of n minus 1 over n minus 3, which makes a difference because the number of repeated indications in metrology in lots of areas of science is rather low. If we are in a luxurious position where we had n equals 30 or 40, it wouldn't matter. It wouldn't matter. But it does matter when n is small. In fact, when n takes the minimum value, in order to apply that formula, n equals 4, it's root 3 times as large. In other words, 1.7 times as large. The standard uncertainty in the revised GUM as compared with the standard uncertainty of the current GUM. That's a big consideration. That's type A evaluation, of course. But type B evaluation isn't going to change at all, and I merely illustrate some concepts here. In all cases, we take the standard deviation of the assigned distribution as the standard uncertainty. And in working with type A evaluation in this way, we're doing exactly the same. We're assigning a distribution to the quantity concerned, we're taking its standard deviation as a standard uncertainty. And so type A evaluation and type B evaluation fall into the same hat. So we treat all input quantities similarly, we obtain a knowledge of a quantity, we apply the appropriate rule, and we derive a probability distribution of the quantity, from which we take the expectation as the best estimate, we take the standard deviation as a standard uncertainty. Obtaining knowledge of the quantity is obtained by domain experts, experts in the particular area of metrology. Apply the appropriate rule, we give guidance in GUM Supplement 1. Derive probability distribution for the quantity. We know that uncertainty budgets typically state the probability distributions used. So in that sense, we're doing nothing new. Example, a quantity between lower and upper limits and a single measured value. That's the only available knowledge we have of that quantity, a lower limit, an upper limit, and a single measured value. We apply the principle of maximum entropy, and we get a doubly truncated exponential function for our probability distribution describing that quantity. There's an example in the current GUM. It's well hidden, and you'll find it, but you have to look. Coverage intervals are going to be obtained much more reliably, obtained on the basis of the distribution for the measurand. When the measurement model can safely be linearized and the central limit theorem applies, y can be taken as Gaussian, and we can use the usual rules. For a non-Gaussian dominant input quantity, such as a t distribution, a rectangular distribution, y, the measurand, is particularly influenced by the distribution for that quantity. In other circumstances, we can get a pessimistic coverage interval for the measurand by applying well-known inequalities from classical statistics. There's a Gauss inequality which applies for a symmetric distribution or Chebyshev inequality for an asymmetric distribution. And if we use the factors there, k equals 3 or k equals 4.5, we can apply a coverage interval which doesn't depend on the distribution whatsoever, apart from the knowledge that it's symmetric or not. Or the resulting interval might be too conservative, and we can apply GUM S1, supplement 1, in that case, to obtain a good approximation to the distribution for the quantity concerned. I'll finish with some consequences for NMIs in industry. Type A uncertainty valuation, we're providing a modified formula, but it's already given in GUM supplement 1, but it's essentially no change for sufficiently large n, but it will have an effect in practice by that standard uncertainty being larger than the standard uncertainty with the current GUM. At least n equals 4 repeated indication values are required, which corresponds to good measurement practice. What do we do if we don't have n equals 4 repeated indication values at least? We have to take recourse to historical or other information. We can't really rely on a standard deviation of n equals 4 repeated indication values. So already advice in the current GUM on that. Some people talk about uncertainty of the uncertainty. The revised GUM regards this concept as nonsense because we deduce standard uncertainty. We take the standard uncertainty as the standard deviation of a distribution. So in that sense, we evaluate a standard uncertainty in terms of our available knowledge of that quantity. Further consequences: degrees of freedom are no longer viewed as a measure of reliability. Degrees of freedom in a type B evaluation doesn't exist, although in the current GUM there's an example to illustrate that fact. The calculation of a coverage interval no longer depends on effective degrees of freedom evaluated using the Satterthwaite formula. A coverage interval for the measure and is computed in terms of the knowledge of the distribution for y. Concluding comments: standard uncertainties are likely to be larger than those obtained by following the current GUM, which in certain areas may assist. A lot of laboratories are involved in key comparison exercises where measurement standards are compared across the globe. And we note in a lot of those key comparison exercises there's a very large number of cases where the data is mutually inconsistent. Increasing the standard uncertainties in the way we're going to may assist for some of those key comparisons. Our aim is, by December this year, to have a first committee draft circulated for review by the JCGM member organisations, the National Measurement Institutes and other invited recipients. There's an online survey we carried out at the end of 2012 to solicit comments and opinions on the GUM. We analysed the survey results and we considered them. The main outcome of the comments, and it reminds me of a comment earlier today, the GUM was criticised by some as too difficult, by others as too simple and old-fashioned. And I think we got it about right by sitting in the middle of those extremes. In the same vein, this presentation is intended to stimulate discussion. We require as much feedback as you can give. Thank you. Well, we say it's unwise to rely on those 2 or 3 measurements. You must have some other knowledge of the quantity you're measuring, which...
You are receiving an instrument for calibration. You have no prior knowledge. And you want to save on money. And the minimum usually that people that so far are 3 measurements.
But
3 measurements is not working.
But consider this. Take a normal distribution, take a sample of 3 from that distribution.
It's on the board.
Oh, yeah. Exactly. Take a sample of 3 from that normal distribution, compute the standard deviation. Do it again, do it again, do it again. The distribution of the values of standard deviation differ widely. You can't rely on one sample of 3. You have to have some other knowledge, prior knowledge.
Okay, so the consequences will be that people will start doing 4 repetitions for each one.
That may be a consequence. But this is the advice we're giving. You have an opportunity to react to this advice when the document is circulated. And I've given this talk 6 times over the last 12 months. Your question was asked at every event. And so it's obviously a burning issue. It has to be addressed. We're giving some advice. If the audience or if the potential users of the revised GUM don't like the advice, they've got an opportunity to comment. But if they don't like the advice, they've got to suggest something better.
My question's related to that. You didn't like the uncertainty of the uncertainty, but I quite like it. I could be persuaded to not like it. But if I'd done the 4 replicates many times,
Yes?
then over time I could be convinced that the standard deviation was small and stable. Then I could justify taking only 2 or 3 because I'm still not sure about the mean, but I could say to myself, I think that's the uncertainty. But that's what you said is inside information.
Yes, but if you've performed this experiment many times, you've got a track record, you've got historical data. You should use that historical data rather than the latest 3 measurements.
So that's exactly the answer to the people that want a small sample.
Yeah, yes, quite.
Okay, I have 3 items. I'll start with the minor one. When you say the unknown y, the probability of this being in the coverage being 95%, I jump back because the interval is the random variable. Y is either in it or not.
Yes.
So it's the probability of the interval covering the unknown.
It's the probability that the true value
But the
lies
value
in
is
that
either
interval.
in an interval or not.
It is, but it's the probability that it's in that interval.
It's the probability that the interval covers it,
Yes.
which is a slightly different formulation. But two other things. One is the multivariate aspect. You mentioned this as a drawback. I see it's not been addressed, if I understand.
Not in this talk.
Yeah, but in the supplement.
In supplement 2, we talk about a coverage region, for instance.
Okay. So we'll look into this.
Yes.
The third thing is related to something that was actually asked before. If you now emphasize prior knowledge, okay, so you say, we would like to reinforce your use of prior knowledge, would like you to go into this, and it's like this problem elicitation thing I mentioned.
Yes.
We don't really have good methods for eliciting prior knowledge. David Cox, he used to say, you want to set probability, then play, use a game and see what's the odds and try to compare the odds to, so you can, okay, that's as close as you can get to some methods for eliciting prior knowledge. Is the GUM helping in eliciting prior knowledge?
Well, I'm trying to include something in the revised GUM on this, but I'm meeting some opposition, mainly because we've yet to find a concrete example in metrology where uncertainty or knowledge elicitation has been applied. It's been applied in many areas, like environmental areas, for instance, when the domain experts is asked for information, say quartiles of the quantity concerned, his best estimate of quartiles of the quantity concerned, and sometimes a panel of domain experts is involved, and their estimates are aggregated, and you build up knowledge of the PDF for that quantity. I very much would like to think that's applicable to metrology, but I've asked some experts, but they can't find a way of introducing that knowledge into their particular domain. I very much like to, and if someone could point me to some material how we could use uncertainty elicitation metrology, I'll be delighted, because I think it has a future.
The existing and the new version relate to properties measured on a continuous scale basis.
Mainly.
What about ordinal scale, ordinal properties?
Well, we discussed this at the most recent meeting of the working group, last month in fact, and we suggest the revised GUM shouldn't cover ordinal quantities, but a separate supplement should be developed on ordinal quantities.
I will be glad to participate.
Oh, you're very welcome, sir. Would you give me your card afterwards? Yeah, thank you.